Okay, so I will be presenting Granville Park Stadium. The architect will design partnership. Structural engineer is Northrop Consulting Engineers. The builder is Belmadar, client Cumberland City Council, timber supplier Rubner Holzbau, and completion will be end of this month. Granville Park Stadium, now named the Eric Tweedale Stadium, is situated in Granville, Merrylands area, around 20 kilometres west of Sydney CBD and 2 kilometres south of Parramatta. It is situated in Granville Park between the busy Woodville Road and Merrylands train station, and is considered by Council as a facility that will address the severe shortfall of the community recreational facilities in the Granville area. The stadium is integrated with the existing parks, playing fields, water splash park, shared pathways, and outdoor recreational facilities. The project evolved out of Council's open space and recreational strategy. The strategy determined the need for improved social infrastructure in Granville, an urban requirement for a multi-purpose community facility with flexible space for a wide range of activities and programs. The project has also been well supported through community consultation undertaken before DWP's engagement. The location for Granville Park Stadium and proposed model briefed by the client meets the best practice requirements for a regional park facility. Key to design was facilities connection to its local environment, to history of Cumberland Plains and current context of the site. The Cumberland Plains were also home to several clans of the Darug people. Aboriginal people feel a belonging to land rather than ownership of it. In Darug culture, individuals also had an obligation to look after the place where they were conceived or born. This includes its plant and animal life. Depending on their time and place of conception, children were allocated totem animals to respect and protect. Warali Wali, possum in Darug language, is a traditional totem of Darug people. The Granville area was widely forested and was a resort for timber getters, charcoal burners, and men who trapped the prevailing native dogs. The original name for Woodville Road was Dog Trap Road. In 1850s, the construction of the Sydney-Parramatta Railway brought large-scale deforestation, and much of the usable timber was cut out by the 1860s. Architectural form of the stadium was inspired by the modest nature of Aboriginal architecture, which was a product of highly complex relationship between the physical and social environment. Also, Aboriginal culture and posted totem of Darug people and connection to the land that was heavily forested. Selection of colours and raw materials was inspired by history, heritage and natural look, as well as the building's proximity to massive grey and red gum trees just to the west of the proposed building. A distinctive material choice was the use of structural Glulam timber beams, struts and purlins for the main roof over the 760-seat grandstand and level 1 function space. Selected for its natural feel, Glulam timber relates to the building's context with its warm earthy glow, softening and complementing the interior materials and making the space more natural and welcoming that will appeal to the wider community. The primary engineered timber structure supported by Glulam columns and beams is European spruce. Site plan. As mentioned before, Granville Park Stadium sits in Granville Park between Montrose Ave to the west and Playing Fields and Woodville Road to the east. Upgrade of the existing pitch was also part of the project, and the pitch is now upgraded to the national rugby guidelines. So that's the location of the pitch. Granville Park Stadium is surrounded by car park to the west and north and beautiful established gum trees that sit between the car park and proposed building. Ground floor plan includes 4 unisex change rooms, referee change room, first aid room, admin, equipment storeroom, and public amenities. It also includes a multi-purpose room and canteen. Multi-purpose room will be used as a gym, but also as a meeting room or space for local community. Level 1 incorporates function space for 150 people, commercial kitchen, and open viewing deck. Together with Northrop, we looked at the different options for timber roof. Option 1, showed here, had a continuous timber beam and less heavy fabricated steel. And I must say this was preferred by structural engineers. However, this option was disconnected with the planning of level 1 and was not my preferred option. Option 2 was a simpler roof structure and worked really well with the planning of level 1, but unfortunately has a considerable amount of fabricated steel at the cantilever connection along grid 2. Due to production and shipping reasons, Rubner, the supplier, split the project in 3 different phases. The phases were also determined by installation procedure. So the first phase was erecting the elements that stand between grid lines 2 and 3. So the structure is stable and braced. And the second, erecting the front cantilever after the rest of the building is up. And then the third phase, installing the timber soffits. So phase 1 showed here, columns and rafters and back cantilever are installed, and temporary bracing system was also installed between the columns. Phase 1 also included installation of roof bracing that did not interfere with beams along the grid line 3. The beams along grid line 2 would be installed only after the front cantilevers were installed. Front main cantilevers and roof purlins were installed next, and how front cantilevers were temporarily propped before the timber fascia towards the field was installed in order to avoid uneven deflection during the installation. Nick will talk about in more details after me. After the front cantilever was installed, the beams along the grid 2 were installed, and after that the roof bracing was installed. After that, the roof purlins were put up. And then a phase 3 installation of ceiling panels and ceiling purlins, so you can see in green underneath. Now we'll look at some construction photos. Unfortunately, we did not have much luck with the weather over the Christmas period and in December when phase 1 and phase 2 were on. Because of a lot of rainy days. So the drone photos that I'll show and that were supplied by the builder were mainly phase 3. So looking from above, that's grid 2, grid 3. So this portion was first installed, and then the cantilever over the grandstand seating. View of the stadium and a Parramatta in distance, and the field. Looking at the construction site from the field side. Installation of purlins. As timber columns were also part of interiors, great attention was made to design of the columns steel base at glazing locations, as well as to the steel base for the other columns that are not embedded in walls. So they look different. These are the bases that we have glazing on each side. So we couldn't work with this base because we wouldn't have a steel connection. Installation of bracing. You can see a lot of water, a lot of rain. Interior. A warmth and brightness was created in the interior by leaving the wood and raw materials exposed. The interior palette is very simple and restrained. Rafters and timber columns are exposed in the interior of a function space on level 1, and raw polished block walls are final wall finish on the ground level. Sustainable design was an important objective of the project. The goal was to demonstrate and achieve that this scale of building can be a highly sustainable development that is low carbon, low waste, and highly energy efficient. The east-west orientation of the building allowed for natural cross-ventilation of the ground level change rooms and passive solar shading due to the large deck and eave overhangs. Rainwater tank was installed underground between the building and car park to provide water for irrigation of landscaped areas and toilets. There is a provision for photovoltaics and metering to monitor and reduce wastage. Use of mass timber construction for Granville Park Stadium is the first use of Glulam timber for this type of a facility in Australia and represents an impressive achievement in timber engineering. Thank you.
Thank you, Ivana, for your presentation. Welcome to Nick. Over to you, Nick.
Hi, everyone. Hope you can all hear me. So I'm going to talk about the structural engineering component of this project, and in particular, just about long-span timber roof structures. A little bit about us first. So Northrop have been working on mass timber buildings for about the last, I think, 8 years or so. And that started with us peer reviewing the International House building in Barangaroo. So that was done by Lendlease. And we learned quite a lot of good lessons off that and really developed a passion for working with mass timber. Since then, we've built 2. So the Carlton Connect initiative actually in Melbourne is a 5-story office building with a sort of semi-open childcare facility. So it'll be the first childcare facility in a timber building, I think, in Australia, and that's sort of underway at the moment. We're just completing the fit out now, and the Honeysuckle building is a 4-story commercial building in Newcastle. So that's the first in Newcastle. So we're just finishing that off as well. I think the keys have just been handed over. We're also working on 2 new timber projects that are sort of pushing the boundaries of timber construction. So one of these is a very large office building in Melbourne that will have one of the biggest timber floor plates going around, about 2,500 square metres over 8 levels. And the other is a timber steel concrete composite, which some of you may know as the Vrede Strong Floor system. This sort of work with timber building is really in line with our company values on carbon neutrality and climate resilience. So we've made these goals in line with our declaration with the Engineers Declare climate emergency declaration. So we're aiming to be advocating for carbon neutrality by 2022 on every project. We'll make it our design philosophy as default by 2025, and we'll be aiming to have all of our projects designed to be carbon neutral by 2030. So we offer all disciplines, and while I think these 3 have fairly significant operational requirements for actually operating a building, in terms of structures, as most of our energy is in that sort of embodied material state, I think timber buildings really plays a huge role in this commitment, both for us and for the industry. There's not really a better way to achieve carbon neutrality than by designing and building timber buildings. So on the Granville Park Stadium, Northrop were engaged for all engineering services from the very beginning. So that includes, I mean, this is a list of all of our services, and the ones in bold are the ones we're doing. Some of them I didn't actually know existed, but we managed to provide all of these ones on the Granville Park Stadium project successfully, which was it's been a really great project. But yeah, just a little bit about me. I'm a structural engineer, so I'm going to be talking about structural engineering only, with really a keen interest in timber. So I've been the peer reviewer or sort of project verifier and leader on these projects, but as a disclaimer, I wasn't actually the lead engineer on this project. She was a really talented timber engineer who has since left the engineering profession to move to the Northern Territories and start teaching high school. So I'm hoping that, I think this presentation, when I send it to her, will encourage her to come back. So just on the preliminary design, Ivana spoke about this a fair bit in the previous presentation, but just to sort of elaborate on the structural systems, the first floor and grandstand is a conventional reinforced concrete and post-tension concrete floor, and the foundation system is screw piles. So there's nothing really that I suppose different from a structural perspective in terms of the podium level. But above that, the roof structure is entirely timber, or sort of 95% timber. It's a system of glulam purlins, rafters and columns with steel roof bracing. The roof itself, there were really only two options that Ivana touched on before. It was fairly well developed in terms of the architecture at the beginning of the project, so the structural scheme developed really quickly. There was another option which has some advantages in terms of reducing the semi-discontinuous cantilevers by having that sort of rather expressive shape, which I guess conventionally wouldn't be an ideal structural system, but to achieve those sort of cranked beams at the cantilever, this option, the bottom option below, allows us to do that without having cantilevers that are semi-discontinuous. As Ivana mentioned, that wasn't proceeded with on the basis that it just didn't really look like the right building that she was after. The structure of the roof and ceiling, so I went through a few different sort of options. It started off with roof sheet on steel purlins, sort of conventional Z section purlins. It then moved to sheeting over CLT, and we tried to CLT soffit finish, or at least a timber soffit finish. But for cost purposes, that then came back to being sheeting on timber purlin. So it achieved our goals of having a timber structure while being, I think, a little bit more of an efficient use of materials than putting CLT panels over the top of the rafters. The CLT panels were intended to provide that timber aesthetic to the soffit, but that aesthetic was eventually provided by fixing a mini CLT panel. So it's sort of like a plywood with only 3 layers, around 15 mil thick, to the underside of the timber purlins. And as you can see there in the image, it's fairly, it's pretty much indistinguishable from what would have been a CLT roof slab. Structural design challenges. Really the main one, which is probably fairly obvious, is the large spans and the cantilevers. It's a pretty significant feature of the building. So the large internal span is 13.7 meters and has a cantilever of 8.3 meters, measured perpendicular, I think, to the main span. So it's actually a little bit longer when you actually take into account the angle of those beams. But from a design perspective, or a member design perspective at least, it's pretty simple. The beams were just sized to satisfy deflection and strength criteria. Nothing particularly unusual there. But they are pretty big as a result. So they're about 1,000 deep by 240 wide. And they taper down to 440 deep at the ends. So they're pretty big timber beams. Another challenge was the double cantilevers at each corner of the roof. So the roof cantilevers over the podium itself, and this sort of double cantilever, you can see that connection there has 5 incoming members. That's pretty difficult to do in timber while maintaining continuity across that connection. So we proposed to hang the corners with a steel beam just nested up in the purlin zone, which was about 250 deep. and to use a structural edge beam on the other end to support that double cantilever. So that was our sort of first option, and it really came down to just using materials where they were most effective or most efficient, really, that we were proposing to use the sort of optimum strength, or the increased strength and stiffness from the steel beam, to just overcome any sort of natural limitations in the timber. But as we'll see later, that was actually removed. The other challenge was the discontinuous cantilevers, and by that I mean basically having a splice in the high negative moment region, or where the stresses are greatest, right over the top of that column, having to splice in two members instead of just running that main primary beam straight out over the cantilever. That's sort of what I'm referring to as the discontinuous cantilever. And they're very difficult from a connection point of view, because it means that you just have very high forces at a node point where we need to then sort of connect that into a timber member. And I'm sure, as most of you know about timber, a lot of it is, in terms of size, governed by the actual stresses you can get from steel into the timber due to the actual bearing of the bolts and the edge distances required. So our solution to this was to fabricate a 5-way steel node. So you can see there that we've got five plates that are welded together that are then bolted into each incoming timber beam. And that's a fairly, I suppose, costly and challenging thing to install. But it is, I suppose, a very safe and effective way of providing that continuity through that connection. As with all timber projects, there are always questions about durability. So this was solved basically by providing flashings to protect timber from direct wetting. So the timber is exposed on the underside, but on the edges of the building there are flashings that come off the roof and down to protect the timber from rain. And at the base of the columns, they're protected by the large cantilevers. It's not going to get a lot of wind-driven rain coming in that far, and they're raised off the ground by galvanized steel feet. So that protects water from coming in along the slab and up into the end grain, which is the most vulnerable to damage due to wetting. It also provides some termite protection. So best practice is to take all the timber up 1 story at least, if you've got a timber building of this size. But in addition to that, these exposed galvanized steel feet just give a really clear observation mechanism for the timber, or for termite trails if there are any. So the project sort of started with local supply, and it was developed with local supply, but for cost reasons, it became apparent that we were going to get a better price going international. So through the local agent for Rubner, which is the Fascia, the supply of the Glulam changed to Rubner, which is based in North Italy. So they then took on the project and completed the detailed design, produced shop drawings, and we peer reviewed that in a fairly, I suppose, rigorous manner, more than you would do for, say, a locally certified project, because we were the eventual certifiers of the roof, and we certified that design. So a couple of things that changed in that process. Rubner optimized the cantilever connections. So what I spoke about before with that 5-way embedded steel plate was changed at this point into this design. So I guess we were providing a design that was fairly conservative from a cost point of view. This was an optimum design, and you can see it here being all fairly aligned with the philosophy of doing as much in the factory as possible. So these steel plates were embedded into the timber beams. There was 1 for each incoming timber beam. They were embedded with basically a significant number of dowels. So I think there's what is that, 16 dowels on the top and bottom, just to hold that plate in. And then it really turned what was a fairly complicated carpentry process of installing all of these bolts into the timber into what was really more akin to steel erection. So it's putting everything up and doing up some tensioned bolts. The double cantilevers were also changed. So instead of hanging a beam over the top and hanging the cantilever off that, the option was instead to put in a steel plate over the top and screw it down. There were some, I suppose, issues with doing this in the eventual building that just due to manufacturing tolerances, it required there to be a full bearing connection at the bottom of that, at the bottom of this cantilevered timber beam, which is actually quite difficult to do with timber because there are 2 millimeter tolerances that are allowed everywhere, just for variability in the actual fabricated size. So it ended up being that once this was installed, it just drooped a little bit until that tolerance was taken up. So there was a bit of adjustment that needed to be done in this connection to try and shorten the length of this strap to take up the tolerance of 2 millimeters in the end of that beam. So, but it was a good solution in the end, and it worked pretty well. And due to limitations in container length, the original beams, which were designed as being continuous over that 13.7 meters, that's fairly achievable in Australia in terms of transport length. But once it was being shipped in from overseas, transporting something of that length becomes quite costly because it needs to live on the top of the container ship. Whereas to fit it inside a regular container, the beams were all spliced. And this was a splice connection that was used. It's similar to the other connections. It's some embedded steel plates that's all done in the factory. And then when it comes to actually putting it together, it's just a couple of simple bolts. Because it was located in a low moment region, it was fairly intelligently located away from that 5-way connection. The number of bolts was actually quite small. So you can see it's only 3 bolts there. That doesn't achieve the full capacity of the section, but the moment of that area is really low. So that's something that just really needs to be considered when designing timber splice connections, because it is quite difficult to splice something to the capacity of the beam. Certification then became fairly tricky because the structure has to be designed and certified against the Eurocode. This is due to a number of reasons, some of them being fairly minor. So the timber supplied was European species of softwood to European strength standards. So you can use other species of timber within AS 1720, but that requires quite a significant amount of testing. It was fairly more straightforward to just use the Eurocode and use the strength standards that are embedded in that. And a fairly sort of simple limitation of AS 1720 is that it doesn't allow for screws that are larger than 7.5 millimeters in diameter, and it doesn't allow for smooth dowels. It only allows for bolts and coach screws. And that's because it applies a more test-based or empirical-based method for the design of connections, whereas the Eurocode moves back to first principles and allows for screws of any diameter and smooth dowels and other different types of connections. So due to those limitations, we had to use the Eurocode, and it meant that we needed to prepare a performance solution to provide to prove equivalence between 1720 and Eurocode 5. And that was a bit of an exercise to try and, I suppose, understand the differences between the two standards and between the two materials that are referenced there. But eventually we found that you really get a very similar capacity using both standards. We did use the Australian loading standards, which made it a little bit easier to prove this performance solution. A couple of challenges during construction. There weren't really many. It all went together pretty smooth. So the temporary stability engineering was carried out by the timber installation contractor, which was Savcon. They did an excellent job of putting this building together. Basically didn't have any issues at all. Yeah, the temporary stability engineering was carried out by their engineer, but there was a request to not prop the end of those cantilevers that stick out over the grandstand. So we had to go back into our model and analyze the roof structure with only one of the beams installed, which was pretty, I think it resulted in a pretty significant amount of deflection until the other one was installed and sort of balanced the whole system out. And we got away with that by just propping that cantilever and taking it out in sort of a push-pull mechanism at the top of that splice. So that meant that the installation was much easier without having to put a prop in that was sort of would have been around 4 or 5 meters tall at the end of that cantilever. It was just designed so that only one needed to be installed at a time. It induced some bending into the column below, but that was all fine. And the last one was timber checking. So checking is a natural phenomenon in timber. It's caused by differential shrinkage due to drying. So when timber starts to dry, it dries more on the outside and starts to shrink, and as a result, it just results in what appears to be a crack sort of opening up from the outside of the timber to the inside. This effect is fairly limited in Glulam because it's made up of a number of different pieces glued together. So each of those pieces will try to check in and of themselves, but it's very unlikely that a check will align between multiple pieces of timber and actually cause anything bigger than sort of 5 to 10 millimeter deep check. So it usually doesn't really present a structural concern in Glulam because of that reason. It doesn't go very deep. I recently went out to a heritage building that had ironbark columns about 300 mil by 300 mil as single members, and they had checks in them that you could put your hand into. They were pretty large. That doesn't actually happen with Glulam. If it does go deeper than sort of 15% the width of the member, that's when it should really be sort of reviewed structurally, but it's fairly rare for that to happen. It does seem to happen just prior to handing over a building, though. It's just one of those Murphy's Law type situations, which means that my recommendation is really to get this all understood by the building owners and by the builders before commencement of the project, because it is a naturally occurring phenomenon. There's nothing you can really do about it. Even fixing it is fairly challenging. If you go and fill that check up with some kind of brown coloured putty, you'll end up with, as it continues to shrink and swell during the seasons, you'll end up with that stiff material inside actually making some of the checks even bigger and potentially causing an actual structural issue. So it's impossible to fix, or it's challenging to fix, and it's something that just needs to be understood as a sort of way that the building performs. So that's a photo of it. We're very proud to have worked on this building. As Ivana said, it is sort of the first of its kind, and it is something that we have advocated for, sort of in getting Rubin involved and really pushing to get this project built in timber. And we're immensely proud that it's been done, and are very happy with the result. Thank you.
Thank you, Nick and Ivana, very much. We've got plenty of time for questions, so please feel free. I'm going to ask a question to both Ivana and Nick, and to answer as together. Is just a bit more on the involvement of the timber supplier, so Thicke Rubin. So how do they help in the process? Because obviously you've done a design and stage. So what was their value or assistance they gave?
So they got involved after, I suppose, all the members were sized and all the connections were detailed, and that was really done for tender, because those sort of details make quite a significant difference. But at the end of the day, they have an office in Italy that really only produces timber engineering, or sort of mainly produces timber buildings and timber elements. So they are experts in the field. So as a result, they come along and provide a lot of guidance in terms of appropriate sizes for members. You know, they will check everything in accordance with the Euro codes. And in addition to that, probably the main element is that it's all within the capabilities of their machinery to produce something that is cost effective. You know, they know all of their CNC machinery sort of back to front. They know what it can do and what it can't do. So I think it is a fairly essential part of the timber project to get to have involvement from the suppliers.
And the earlier involvement is probably going to give you a quicker path to the final design. Is that normally what happens?
Yeah, absolutely. Like I think, you know, they can provide pretty early advice on design of on the design of the members, and sort of push the design along a bit more quickly. I suppose like any sort of competitive tender process, there needs to be a benchmark that is provided by a sort of independent consultant. But yeah, like similarly, if they get involved early, you get a good result.
Ivana, your experience?
It was really good. Rubna Holzbauer, they have worked with Australian engineers before on Miracle Library, Chatswood in Melbourne, then Aquatic Centre in Canberra. So they knew some of the requirements for Australian compliances and all that. It was a lengthy shop drawing process, and I was just a bit stressed that, you know, you have to make sure that everything is done properly and everything is accounted for, because when timber comes in, you can't just order another one and replace it. So it was just lengthy process, but at the end it was perfect and there were no issues on site. So
great, thank you. All right, let's go into the questions, and I'll just go in the list as I see them. They may not be in order of written, but how long? Firstly, what are the total costs and duration of the project? If you don't want to disclose the total cost, don't. But duration of the project? Duration
12 months, and the project is between 8 and 10 million.
Okay. Gavan has got a question. How do they determine the depth of checking? So probably one for you, Nick.
So I don't remember the exact size, but you use I think it's a 0.2 millimeter feeler gauge, and you just stick it down the crack and then measure the depth. So yeah, if anyone's interested, you just go to Bunnings, and it's like if no one's used a feeler gauge before, it's a set of real narrow metal strips that they use a lot in car engine manufacture. You just buy one of them and stick it in the crack. Yeah,
or if you haven't got one, I use a business card. Tends to do the same thing. There you go. Okay, Anne's got a question. What is the finish on the exposed fascia and rafters? And was there any exposed fascia and rafters?
We have a flashing over the end rafters and fascia, so just colourblind flashing. So
okay. I think in some of the photos they were still during construction when that fascia was installed.
Yeah, I think now it's finished.
So I'd like to say, was there any direct weather exposure to any of the timber?
Timber was exposed to weathers during the Christmas break because it was just, it was during installation and sure. We had a lot of rainy days, but part of just natural staining of timber, we didn't have any other issues.
And the finished building, it's all covered up by fascia and roof, is it?
Yes, yes. Yeah.
Okay. Question we've already talked about, but I'll ask again. So Franklin and Robert want to know what type of timber was used for the construction element and where was it produced?
The timber, so the company Rubner Holzbau is Italian-Austrian company. The timber came from Austria and it's European spruce.
Okay, thank you. So Sam has a question. And any particular programs used to calculate the capacity of the Glulam members?
No, just a spreadsheet and a calculator. It was all done in accordance with the Eurocode. Yeah, there was nothing in particular that we used to automate that.
Sure, I'm sure you would use the properties from the Glulam company.
Yes. Yeah. Well, their properties are derived directly from the European standard for Glulam manufacture. I don't recall what the actual grade was. I think it might have been GL28H.
Okay, just for people who want to know where you get properties from companies, each supplier has an ETA. In the ETA, there's always the properties. There's a declaration by the manufacturer, so you can always find out what they produce or have from that information. Kieran has a question. It's got one for you, Ivana. Was a maintenance plan specified?
Yeah, it came from Rubner, and then through Belmada, it will be handed to the client, but nothing in particular, just reapplying the coating to timber. I don't know if it's once a year or every 2 or 3 years, but that's it. Nothing really special.
Okay, excellent. One from Colin. How was the timber that was used for the fascia and beams protected from moisture? Okay, we've probably done that one by fascia, so we'll move on. David, least advice were questions was, sorry, it's not making any sense. Gavin, can you confirm how they determine the depth of in checking installed beams to determine whether it is minor or major, I suppose?
Yes, so that I believe it's 15% of width, and it depends on where the checking is. So typically it just runs along the grain. If it's the underside of the beam, it doesn't really do anything. So we usually just apply a sort of 15% of the depth sort of figure as being something to actually try and look at or not. If it's in the side of the beam, that's more likely to be significant because it obviously, if it went all the way through, it would split it into 2 separate beams with half or whatever it is, a 1/16 of stiffness. So yeah, it's the same sort of procedure. It's still usually 15%, but that one is easier to do a calculation on, and that calculation will be more significant. And same with the column. The guidance, I believe, comes from the American Wood Association. There is a document about that for building owners that answers questions that they may have about checking. I think if I was to provide a document to a client to say, here's a good explanation of checking, that would be what I'd send them.
Okay, and I'll probably just add, from my experience, how to avoid or minimise any checking is when you store the timber, you don't use use a vapor permeable type of wrapping. Don't use impermeable. Impermeable wrappings and dark colour wrappings will just act as a greenhouse and won't be good for the timber. Other thing is also ingrain protection. So you may see it on a lot of CLT buildings. They use what's called a magic tape. The magic tape is just covering the ingrain. So if you can limit moisture transfer from ingrain, think that the reason why the timber is just a bunch of drinking straws, so it's going to drain out from the ends, and that's where you're going to get your checking occurring from the ends normally. So try to minimise the moisture transfer at that point. So it's, again, if you need more advice, our Wood Solutions and mid-rise team are experienced in all these sort of things. So please give them a call and contact them. We had a question from Barry. He wants to know what software was used. So I assume that you're just talking about standard engineering spreadsheet software.
Yeah. So yeah, we use Space Gas to analyze it. I'm not sure what Rubner used actually. Yeah, I'm not sure. It was something similar. It didn't do any particular amount automation in terms of timber design.
I think there's thousands of engineering programs with timber in it. Every engineer has their own. And one from Patrick is probably one for Ivana. What is the final seal painting finish on the CLT lining panels, or was it factory supplied?
Yeah, it was all coating was done in factory before it was shipped to Australia. But what actual product it is, I'm not sure. It is something that Rubna supplies, so I can't give you the answer on the actual product, but yes, it is done in a factory.
Yeah, I would also recommend we call it a construction coat is put onto the timber. It just helps in handling moisture during the transportation and storage and erection on the site. Because as we all know, a mass timber building, it breaks droughts, and as soon as you put one up, it's going to rain. It's always good to have a bit of protection there. Another question from Gavin: could moisture enter the checking over time? Yes, I will answer that. Yes, of course. It's if any water can get on the structure, it's going to also get in the checks. And that's the idea why we minimise that. Moving on. From Sam: what was the design life? What is the expected service life to first maintenance?
Design life is 50 years. About the first maintenance, I'm not sure. As I said previously, I have to look at the maintenance. Can't answer that.
It's okay. All right. So standard design life for a structure like that, and the maintenance schedule is with the contractor. All right. We'll move on. Next question. Probably one for Nick. How do Australian engineers correlate the durability and performance of a European timber? Is there a European standard similar to AS 5604? And Nick, if you need any help, I can help you with that one.
I do need help, yeah, but I wasn't really across that particular part of the solution.
Okay, I'll just give you help on that one. The first thing to know that there are durability ratings from Europe, there are durability ratings from Australia, and they, like the currency between the euro and Australian, they don't match up. So the first thing, don't assume a durability rating from a European rating system is equivalent to Australian one. The correlations for it, there's some search work that's been done to have comparisons between the two. On the top of my head, I can't think of it is, but just be wary that there are different experiences and different exposures. Australia obviously has a higher UV and different environments from tropical through to polar climates, while Europe is much more a polar climate type area. So just be wary of that. We have a timber durability centre in Queensland, and they're good to ask questions on that if you ever want to know. So one from Robert, probably you to Nick. The next question is definition of a discontinuous cantilever, which was a CPD question.
Am I allowed to answer it then?
Yes, of course.
So it's essentially a cantilever where the backspan is parallel to the back. So in this particular project, because the cantilevers were all sort of like a zigzag shape,
yep.
If you look at the plan, that they don't continue all the way back through.
Okay.
I don't think that's the definition. I think I just made that up. You know.
So there's no such thing as discontinuous cantilever, but we got those. I think the answer to that one is the use of the metal connections and plates and that the column node is really giving you that continuity of the forces that through to the wood on the other side. So that's what we're looking for, really. I've got two more questions and we'll wrap it up. There's an anonymous one. Was a reduced stiffness used as at the splice connection in the design?
Yep. So two models were run. I think one full rigid stiffness, one with the rotation ring there, just movement in the jab. Yeah. Okay. As to whether the deflection checks, no. They were checked on the double cantilever actually, because it was noted that the deflections there to connection. So then when that all came back to the original and to sort of tightening up that connection, then it all came back to the design. Expecting.
Okay, it was a little bit broken up there, Nick, but I think we mostly got the answer. And the last question, which I'll answer, is from Franklin. Does Wood Solutions sell 300mm diameter timber poles? We are looking for some soon for a rural project. Wood Solutions doesn't sell anything. It's a campaign by the timber industry. Hopefully, I suggest going to the Wood Solutions website, where in there's a suppliers index, and look for timber poles, and that should be able to direct you to people who sell or manufacture timber poles. So at that point, I'd like to say thank you to Ivana and Nick. Brilliant presentations. I'm just absolutely blown away with that. And there's the CPD questions again, just for people for you. Much appreciated for your time. Just a reminder that this webinar has been recorded and will be available on the Wood Solutions website very shortly. The certificate will be sent email to you very shortly as well, which will again contain the CPD question, and please download and fill in and store in a safe place, so it won't be reissued again. We also have a survey contained with it, and we appreciate it if you could spend some time and fill out a survey, as we want to find out what you want to learn and hear. Our next webinar, it will be on the 22nd of June, and it's been a very interesting one. Professor Jeff Borton from Timber Ed is an absolute nut when it comes to chasing winds, a bit of a storm chaser. So he's going to do a talk on buildings to resist high wind cyclonic forces, a case study of cyclones. So he's well experienced in looking at the damage from buildings following cyclones. So that'll be extremely interesting. So again, that'll be on Thursday next week on the 22nd. Please, actually, it'll be it's Tuesday, the 22nd. Apologies, that's wrong. And I look forward to that. So at that point in time, I'd like to remind you that we actually have a face-to-face seminar in Canberra, real face-to-face, and it will be a bit of an update on where we are with timber frame construction. It will be held in the building, which is centre on the display there at the Merrylands building, which is a 5-storey mass timber building in the Australian National University. So if you're in Canberra, please come along. Just go to Wood Solutions events section and be able to follow the link to register for that. And following in this point in time, I'd just like to say again, thank you to Ivana and Nick. It's a brilliant presentation. It's a brilliant structure. I look forward to seeing it, Ivana, in the Timber Design Awards. And at this point in time, I'll wrap it up and say thank you, and see you at the next webinar or seminar.